This is a tiny piece of metal just 3 millimeters across, and here's what happens if you just keep zooming in. 1,000 times, 100,000 times, 50 million times. Each of these blobs is an actual atom. I saw this the other day at the University of Sydney, and it kind of blew my mind, because up until just 30 years ago, directly seeing atoms like this was thought to be impossible.
Why is it so hard to see atoms?
Well, you can't actually see atoms with visible light. That's because while light has wavelengths between 380 and 750 nanometers, an atom is still over 3,000 times smaller, just 0.1 nanometers. And if the wavelength of light is much bigger than the thing you're trying to see, the light will just diffract or bend around it, so you won't be able to see it.
So if you want to see atoms, you need something with a much, much smaller wavelength. The best candidate isn't even light. It's electrons. In 1924, a French physicist named Louis de Broglie worked out that everything was sort of wave-like. Not just light, but matter too. Atoms, molecules, even you yourself have a wavelength.
And the formula for this wavelength is Planck's constant divided by the whole beam of electrons. You'll see they all get steered into the center, focusing the beam. By 1931, Ruska and his colleague Max Knoll used this kind of design to build the first working electron microscope. It was pretty basic, made of brass roughly bolted together. But it worked. The image itself was created once the focused electron beam hit a sample sitting at the focal point. The sample needed to be incredibly thin, only around 100 nanometers thick. More electrons would make it through the thinner parts of the sample than the thicker parts, creating an electron imprint of the sample. Then a second electromagnetic lens magnified this imprint down onto a fluorescent detector, producing the final image. This was known as a transmission electron microscope, or TEM. Now, early versions of the microscope barely magnified at all. In fact, it wasn't even better than an optical microscope. But Ruska was determined. Over the next few years, he experimented with adding more lenses onto the microscope to create bigger and bigger images. By the mid-1930s, Ruska had gotten the TEM way past 10,000 times magnification. It could produce close-ups of insects, bacteria, and even viruses at a level far surpassing the optical microscope. But right as Ruska's TEM was taking off, a German physicist named Otto Scherzer published a paper that the microscope was about to hit a brick wall. There was a flaw in the electromagnetic lens, he wrote, that was completely unavoidable. For an electron to make it to the focus of the lens, it needs to be deflected by a specific amount. If you simplify its trajectory, you can define that ideal deflection with this angle theta. This angle depends on the horizontal distance of the electron from the optical axis, and how far down the axis the focus is, also known as the focal length. The shorter the focal length, the stronger the magnification. If you graph this angle as a function of distance to the optical axis, you'll see that it can be approximated as linear. The problem is that the magnetic field doesn't scale linearly. It's much stronger near the edges of the magnet. So modern lens systems in cameras and microscopes use some sort of correcting divergent lens.
So you might imagine that the TEM simply needs its own version of a diverging spherical lens to magnify further. But with magnets, this is physically impossible.
Every magnet has two poles, a north and a south. It's impossible to just have one. Even if you split a magnet down the middle, it creates two smaller magnets, both with a north and a south. And all magnetic field lines have to start at one pole and end at the other, forming a closed loop.
Is a direct result of the second Maxwell equation, because the field that you create has field lines that start and end at the same magnet. So the electrons will always cross through two lines.
The first time it passes through by the Lorentz force, it's brought into the spiral, and then the second time, from that spiraling motion, which has then a slightly different direction, it's pushed towards the axis. That's why all electromagnetic lenses, by default, will converge the beam and never diverge it.
Even if you shot electrons in from the other side of the lens, they would still get focused. This is what Otto Scherzer's paper proved in 1936, stopping progress on the TEM. It is impossible to produce a radially symmetric magnetic lens that diverges.
And this was, of course, a big roadblock for the development of electron microscopy, because people saw, okay, we can accelerate electrons as much as we want. The presence of a spherical aberration will always be in the way.
Because of this roadblock, advancements in the microscope's resolution slowed significantly. By 1955, another microscope beat the TEM to the punch and took the first generally accepted image of atoms. This was called the field ion microscope, and it worked by shooting helium or neon atoms at an atomically sharp needle. The tip was positively charged, so when the gas atoms hit the needle, they got ionized and were ejected off perpendicular to the surface. And that could form an impression of the atomic structure of the tip. But this method was limited. You could only get a sense of the atomic structure of the very tip of the needle, and the images weren't all that impressive. Luckily, Ruska's electron microscope wouldn't stay stuck in the realm of insects and bacteria forever.
Now, you might not be an insect getting bombarded with relativistic electrons, but it can sometimes feel like it when you're getting bombarded with spam calls and targeted ads. It's a real problem when we're researching for our videos. I was reading up on lenses and optics, and a few days later, I started getting targeted ads for glasses and eye surgery. So someone out there is probably selling my browsing data. But this is where today's sponsor, Incogni, comes in. With your permission, Incogni will fight the data brokers on your behalf by finding out who has your data, which laws apply, and then they...
Around this time, other microscopes emerged that could also image atoms. These probe microscopes work by gliding an incredibly small stylus across the sample. The stylus detects variations in quantum effects or nanoscale forces to then map the surface structure of the sample. These were easier to build, and because they didn't use any lenses, they weren't limited by spherical aberration. Their images were even 3D.
But the looming issue was that these probes weren't really seeing atoms. It was more like feeling atoms.
Throughout the 80s and 90s, this was all we had. But what if there was another way? Scherzer's theorem proved that a diverging radially symmetric lens isn't possible.
But if you're willing to give up on that symmetry, the theorem no longer applies. The problem is that radial symmetry is arguably the most important property of any lens, because if you break the symmetry, you also break the image.
But 3 maverick scientists thought there might be a way. Knut Urban, Max Haider, and Harold Rose were known in the electron microscope community as troublemakers, and for years, barely anyone had been interested in their research, or more importantly, in funding it.
And for a good reason, too. Their idea was kind of crazy. I mean, they purposefully wanted to break the image using a lens that wasn't symmetric. Their hope was that there would be a small part of this distorted image that would be slightly diverging. And maybe, just maybe, this small part could correct the spherical aberration of the original lens. So they got to work.
To distort the image, they used a massive nest of electromagnets with 6, 8, or even 10 separate coils and magnets with bumpy magnetic fields. These were known as the hexapole, octapole, and decapole magnets. So as the electron beam passed through a hexapole, it would twist and squeeze the flat 2D image into a triangular saddle. And the circumference of the original beam would be pushed into the 3 corners, with the rest of the interior for the aberrations in the TEM. Andrei Krvanek independently achieved the same for Kru's version of the microscope, the scanning TEM. And in 2020, all 4 were awarded the prestigious Kavli Prize in Nanoscience for accomplishing what so many others thought impossible. Through their persistence and ingenuity, seeing atoms like this is, well, normal. How big of a difference does aberration correction make?
If you want to see atoms, and if you want to, for example, measure interatomic distances, and if you want to learn what type of atoms you have, you need aberration correction. Any research that's materials science, materials engineering, chemical engineering, you need to see what's happening at the atomic level, because you want to relate the properties to the structure. If you can't see the structure at the atomic level, you only have half of the information. So that